My suggestion here is that we start by we don't need to go through the introduction, the first 3 paragraphs, but I suggest that we kind of go over this first combinatorial optimization section, which is the first page and 2 more paragraphs, and then we start discussing from there. So maybe let's don't take a few minutes to read through this first part, up until the statistical mechanics subtitle. Does it sound good?
Yep.
Mm-hmm. You guys can tell me when you're ready.
Where do you want us to read to? I was reading on my
Up
own,
until
actually, sorry.
up until statistical mechanics. Yeah.
I'm almost there. Give me 2 seconds.
Sure.
All right, yeah, I'm there.
Okay. How about the other one? Everyone else?
Still need 1 more paragraph.
Yeah, sure. There's no rush.
Yep, I just finished, so whenever ready.
Great. Cool. Mm-hmm. So in general, they kind of just, this is the introduction section, right? They just mentioned that, okay, we have combinatorial optimization. The classic example is the traveling salesman problem. There's generally 2 approaches, divide and conquer and iterative improvement. Both of them have their problems. And they're like, okay, there's this thing called statistical mechanics. We might want to do something with it. And then the next section is going to make a lot of references to physics. And I think to appreciate it, we should take a few minutes and go over and make a quick foray into the arguments that they're going to be referencing. So I just want to pull up like a clean sheet of paper here and go over some things, if you guys don't mind. I think you should just straight up interrupt me if anything doesn't make sense or is weird to you or you have questions. Yeah, but does this plan sound good?
Yep. Sounds good.
Okay, cool. Okay, so the fundamental question that we need to figure out is, let's, oops, that's very wrong. Okay, let's take a look at this sort of thermal system where we have a heat bath, which is just some large object at a particular constant temperature. And in fact, it's so large that if we put another object in it at a different temperature, T naught, and this object might have some particles over here that are moving, and they might be exchanging energy with a heat bath. The heat bath is so large that its energy is not going to change, right? So the fundamental question that we want to answer is to figure out what it means for the system to arrive at a thermal equilibrium, right? So we have some object with some moving particles in it. They can exchange energy with a heat bath, but they don't move, they don't leave or enter the sort of piece of metal that we have here at a different temperature. And we want to understand what it means for the system to arrive at the equilibrium. We kind of have the intuition that, okay, at the end of the day, it's going to be at the same constant temperature, but how exactly what it happens and what it means. So there are two approaches to sort of understanding this situation. One of them is what everyone kind of faces in high school physics as the God, this word is so complicated. Individualist approach, so we want to define what it means for a system to be in the thermal equilibrium. And we just say the individualist approach, sort of 19th century physics, says a system is in thermal equilibrium if it's in a particular pure state. So far it kind of makes sense, but also doesn't. We just say that we define that the system is in thermal equilibrium if it's in particular pure state. We don't yet say what that pure state is, but we just say that, okay, there's one particular state that if the system, if and only if the system is in that state, it's in thermal equilibrium. And this is weird this is a weird way of wording things, but it's important because there is a different approach. And this approach, the statistical mechanics approach, and it's also called the ensemblist approach, is what the paper is going to be referencing. So this approach says a system is in thermal equilibrium if it's in an appropriate statistical state. Given by a probability measure on phase space. So sort of this gets very weird very quickly. So to understand what this is saying, we need to understand first, what is a phase space? Well, actually, that's very simple. If we have our piece of metal, our system is essentially a piece of metal interacting with a heat bath, right? Piece of metal is a bunch of particles, each of which has a coordinate and some momentum, right? P. Right. So we can describe our system in some way, and each of these descriptions of the system maps to a particular point in what we call a phase space. So phase space is just a bunch of points, each of which describes a configuration of our system. Okay, so understand what a phase space is. Now, what does it mean for there to be a probability measure on phase space? That's really weird. What do we actually mean by that? Okay, so what we mean by that is that if we sort of mentally imagine, if we run this mental experiment of taking our thermal system, right, and replicating it in our minds many times over, right? Many times over. And then we actually look at each of them and we I don't know, write down their macroscopic parameters, let's say energy, and we say like, okay, in the first instance it has an E sub 1 energy, in the second instance it's E sub 2, in the nth instance it's E sub 1 again. Then what the ensemblist approach says is that the system itself is in thermal equilibrium if the distribution of these states that it can obtain, the probability of it being in each state is actually defined by some, well, formula, by some particular probability distribution. And we're going to talk about what the probability distribution is exactly in a second. Do you guys have any questions so far?
No, I think.
Okay.
Good for now.
Cool. You'll see how this. So I think the goal for this is to spend 10 more minutes talking about sort of physics and see how we and arrive at the intuition of how we might apply this to combinatorial optimization before we actually read the paper. Okay. So the probability distribution that the ensemblist approach talks about is called the Boltzmann distribution. And let's start a new page. And and it's defined as the probability of being in a particular state X is E to negative beta, where beta is some constant times the energy of the system in the state over some normalization factor. Okay, so this actually might remind you of something, but okay, where beta is 1 over kt, where k is some Boltzmann constant. It doesn't really matter what it is, but what does matter is the T is the temperature. In our case, it's going to be the temperature of the heat bath, the temperature, well, of the heat bath, because we're talking about the thermal equilibrium. And Z, the normalization factor, is going to be sum over all possible numerators, right? Let's say xi. Okay. So let's put this in a box because we're going to need it. Cool. So if from this probability distribution you were willing to sort of describe the expected value of energy, well, then the expected value is by definition just the sum. Oops, let me be more careful here. Of being in a particular state, or probability of being in a particular state times the energy of that state, right? And well, if we did some math, but we're not going to do much math here because we just want to sort of sprint through this argument, this would actually be negative derivative of logarithm of z with respect to beta. And again, z is the normalization factor here, which is the sum of all the possible numerators of our probability distribution, and beta is 1 over kt. Okay. Now, so we have this, and now we want to answer 2 questions. And these are the questions that the paper assumes the people reading it kind of know the answer to, but at least to me, it didn't make any sense until I sort of read up on it. So we want to answer 2 questions. How does expected value of energy over this probability distribution compare with the actual energy seen in experiments, right? Because it's kind of weird if we have some probability distribution of the energy states of our system. Well, okay, you might believe that description from physics, but like when we're in the lab, we only have like one particular state we always observe, and it doesn't really deviate much from one experiment to the other. So what does it even mean to have a probability distribution? Like, how does it compare with, how does it correlate with our actual experiments? And we also want to know, how does our probability distribution change with temperature, right? So we see that the temperature is sort of a hyperparameter that we have over here for our probability distribution, right? But what if we slowly, after reaching a thermal equilibrium, if we slowly heat down the heat bath, and then we wait a little bit, then we heat it down again, wait a little bit again, what's going to happen to this probability distribution? Like, what energy states will our piece of metal actually obtain, right? So these are two quickly answered by looking at a particular example. So far, so good. Do you guys have any questions?
We want one quick question. So the X that you're mentioning, is that the microscopic parameters like the momentums and the positions?
Yes, yes, sure.
Okay, gotcha. And those are what you need to compute the energy.
Mhm.
Does that mean?
Yeah.
Does that mean that like? Actually, I'm trying to think where the randomness comes from. It actually might not be relevant, to be honest. So I'll save the question. But yeah.
Randomness. I think you're slightly ahead of what we're getting into. We're gonna talk about that in a second. There's gonna be example illustrative of like
All right,
how
sounds good.
randomness quote unquote changes. So okay, so let's try to answer these two questions real quick by looking at an example. We're not gonna do a general derivation here or anything, but we'll look at a very good illustrative example. So let's say we have a paramagnet, which is just an object with a bunch of particles in it. And each particle, it has a fixed position, but it might have a magnetic moment, which is either positively oriented or negatively oriented. That's it. It's very simple. Okay, so we have n particles, and let's say, okay, I'm running into notation problems here, but let's say E sub I is the energy of a particular particle. Then E sub I is just plus or minus mu, depending on which way it's facing. We have a very simple system here. Then since n, the total n number of particles in our paramagnet is just the number of particles facing oriented positively plus the number of particles oriented negatively, the total energy of the system, E, is just going to be mu n sub plus minus mu n sub minus. Okay. All right. So let's try to apply our formulas over here. Let's first start by, so we figured out, we kind of omitted the derivation, but we figured out that we can calculate E bar from Z. So it makes sense to start with figuring out what Z is. Well, again, to save us some time, we'll just stare at it. Justin and I were in a class where our professor just told us to stare at problems for a long time before we actually write down anything. But okay, if we stared at Z over here, it just sum over E to we have some coefficient times energy, and the energy is computed very simply. And we know that we want to sum over all these states, and we know that each state is defined just simply by the number of particles facing positively. So you might imagine that we are going to have to iterate over. We're going to like writing out this formula. We're going to say, okay, how many ways can we pick one particle to orient positively? How many ways we can pick two particles to orient positively? Well, if you kind of continue down this argument, you will figure out that this is a binomial formula, and well, we're not going to write it down, but write it out. But what we'll get is minus mu beta plus E mu beta to the power of n, right? Which is actually 2 times hyperbolic cosine of mu beta. Okay, we're almost done. This is very cool. We don't actually have to do math. We just have to look at the formulas. So let's see what E bar, what the expected value of energy then is. Well, as we said, it's the derivative of log Z with respect to beta. We're again, I'm going to write it down over here as a reminder. This is 1 over KT, where K is the Boltzmann constant, just a number. Okay, so E bar is actually going to turn out to be negative n mu hyperbolic tangent of mu beta. Right, that's great. So now we can actually sort of try to answer our first question: how does E bar compare with the actual energy seen in experiments? Well, what does it mean to compare E bar with the actual energy? Quantitatively, that means we want to look at the variance of this distribution, and the variance is defined as E squared bar, or excuse me, minus E bar squared. And well, we're again not going to do any math here, but it's going to turn out to be n mu squared over cosh squared mu beta. And well, the final step that we need to do here is to, so we have E bar, we have the variance, and now to eliminate all unit problems, we'll just take a look at, excuse me, one over the other. And well, this is going to turn out to be 1 over n sinh squared mu beta. Cool. Okay, so these are all the formulas we need. We're done with math for today. Now we can answer our questions. So first, how does E bar compare with the actual energy seen in experiments, right? So again, beta is 1 over kT. So for each particular energy, sinh is just some constant, but we see that as n approaches infinity, if our system is very large, it has a bunch of particles, right? The relative variance tends to 0. Right, so this is kind of almost crazy, but the actual parameters that we might measure in our system are going to deviate in such a negligible way compared to our measurement errors that we don't really care about them. That's why we actually that's why we expect to see all the same stuff all the time when we actually measure something particular about our system, such as energy. Right now, and the next question we wanted to ask ourselves is, how does the probability distribution change with the change of temperature? Well, okay, so we had our E bar. Let's write it down once again. Minus n mu tangent. Oh, this was hyperbolic tangent. Mu 1 over kT, right? So what happens when temperature goes to infinity? What happens when temperature goes to infinity? The argument of a hyperbolic tangent then goes to 0. So the tangent itself goes to 0. So E bar tends to 0. Cool. Okay. We'll talk about what this means in a second. And when temperature tends to 0, what happens? Well, the argument of the hyperbolic tangent tends to infinity, then the hyperbolic tangent tends to 1, and we have the energy tends to negative n mu. Okay, so what does this mean? The only way, in our very simple paramagnet system, the only way for the total energy of the entire system to be 0 is for half of the particles to be in the positive orientation, half of them to be in the negative orientation. And this is what I sort of thought that Justin might be intuiting about all this with respect to randomness, like high temperature, lots of randomness, entropy, if you wish. But and when temperature tends to 0, well, we see that the total energy of the system is negative n times mu, and we remember that a particular particle might have energy plus or minus mu, and if the total is negative n mu, then every single particle obtains this what's called the ground state, the state of the minimal possible energy. It just sort of, the entire system gets stuck and collapses into a single state, right? Okay, so we answered these two questions by looking at a particular example. We sort of understood, hopefully got a general idea what a canonical ensemble is, this thing ensemble, which is just a mental model we have over this thermal system. And now that we have these two derivations, we might imagine that actually, if we draw an analogy between a combinatorial optimization problem and a loss function and our energy of an imaginary metal, and then if we might simulate this probability distribution with some, I don't know, Monte Carlo algorithm, and then we actually figure out how to jump from one probability distribution to the other by cooling down the entire system, then we know that at the end of the day, whatever might happen, in between the process, we know that at the end of the day, the entire system is going to collapse in some very minimal energy state. And that might be useful to us in our combinatorial optimization approach. So now I suggest we go back to the paper and actually read it, if no one has any objections or questions.
Yeah, no questions right now. That was a pretty cool overview. I think I was sort of able to follow, not like all the math stuff. I think that part I'll just believe, but like the concept made sense.
Right. Yeah. The concept, you'll see the like there will be exact sentences that reference these things, and I think it will be easier to read it. So the paper itself is pretty long. I suggest we read the statistical mechanics part, which is where they explain their approach. Then we look at the last section where they describe how they apply it to the traveling salesman. So I suggest we take like 10 minutes to read the statistical mechanics section together. I mean, each by their own, and then we discuss.
Oh, wait, can I ask a question regarding the previous
Yes,
system?
yes. Yeah.
So is basically the idea of this that we're trying to draw an analogy for like cooling down the system and we'll get a stable state?
Mm-hmm. Yeah.
Okay.
Yeah.
Are there like, I guess, any specific parts of this that we should pay attention to with respect to what we're going to be talking about later? Or just like,
yeah, so you'll see that they specifically mention that the measured value of energy doesn't change much from the expected value of energy when n is large. So that's sort of something we just showed experimentally, I guess. They're going to reference this directly, and while they're going to talk about, there's going to be a sentence that's going to say that something like the entire system, the probability distribution collapses into the ground states. Well, now you know what this means. We showed this on an example, that when we cool down the system, it actually does collapse and everything obtains a particular state. That's what we're going to be talking about. Yeah, so that's why we did all this.
right, thank you.
Personally, I'm not the greatest fan of physics, so yeah, we did this because I felt like it was very necessary. But okay, so let's read the statistical mechanics part. Yeah, so in the end, they do a bunch of math again, which I don't think is very useful. You kind of, I don't think it matters if you just skip it. How are you guys doing on this section?
Good so far. I'm like almost at the physical design of computers.
Yeah,
Oh,
me
okay.
too.
Yeah,
But
don't jump into physical design of computers. It sounds great, but just don't.
I just kind of skimmed over the math, but I'm just trying to
Yeah,
get the other sections.
we did all the math.
Yeah.
So any questions, or I don't know, maybe non-obvious things, or
The Metropolis algorithm
comments?
seems pretty neat.
This is, have you heard of it before?
I don't think I've ever actually looked at it. I may have.
Okay, so
it somewhere.
it's an algorithm for, like, if I understand correctly, Monte Carlo is just like an approach, and Metropolis is a particular implementation of it. And what they don't say here is, but what it actually means, the way they implement it, the way the Metropolis algorithm is actually implemented, is that what we actually do with simulated annealing, like in human terms, without all this math, is that we start at a particular temperature, it doesn't matter. We generate some seed solution, which is terrible because we just generated it randomly, right? Then we just start generating its neighbors, right, in our solution space, sort of. And so we generate a neighbor. If it's better than our current solution, then we accept it. But if it's worse, we accept it with some probability, right? And this probability of accepting the worst neighbor decreases as we decrease the temperature. And this is the core idea. This is the actual, like, what we draw from the physical description of metal cooling, right? So we'll see some graphs, but this is the core idea. We kind of, unlike in normal iterative improvement, we allow ourselves to make moves upward, but the further down the process we are, the fewer moves upward we will make. Any thoughts? If everything makes sense, we can look at the examples. At one example will be travel assessment. What do you guys think?
Okay. Yeah, I think we can do that.
Sure. Okay. So most of the paper is the physical design of computers part. It's a fascinating read, but it takes too much time. Let's just skip all of this, and then on the I guess the page before the last one, there's this travel and salesman's section, and it's a few paragraphs long. So let's read it. Yeah, so I don't know how hard or easy it is for everyone to understand what they're saying on the first read. So feel free to sort of share your thoughts with me. I wanted to pull up a different graph. I made a simple implementation of the thing that they're talking about for travel and salesman, and this is sort of a random starting path, and then as we cool down, we can actually arrive later to this much more optimized option. And this is the graph where to the left we have on the y-axis we have the travel distance, and on the x-axis we have the temperature. We just simply simulate a bunch of points at every given temperature, and then we slowly cool down. Well, we get to a solution that's 12 times as our random initial solution. Yeah, so I think the main point of this entire paper that they described in a very convoluted way is that this is the same thing as iterative improvement, but we allow ourselves to make decisions or sort of steps upward where we worsen our cost function. But the more and more we simulate, the fewer steps upward we make, right? And then the less probable it becomes that we accept a worse solution than we currently have. Yeah.
Okay, I think that makes sense. Wait, I guess implementation wise, how would we like randomly generate like different solutions?
Great, that's a fantastic question. Okay, that's a fabulous question. So for this to work well, we kind of want to take our current solution and not just randomly generate any other solution, but generate sort of quote unquote a neighbor. And well, there's some other paper that they mention in here, which suggests that we just kind of the way I did it and it worked. You randomly take two indices in your travel and salesman current solution, right? Which is just a vector of cities in some order. And then you reverse the subsequence bounded by these two indices, right? So if you have like, I don't know, 1, 2, 3, 4 cities, then you randomly pick 2 and 4, and the next neighbor is going to be 1, 4, 3, 2. And then you either accept it if it's better, or you non-deterministically accept it if it's worse than the current solution.
Okay, sounds good. Seems like so. So would that be like domain specific then?
Yeah, it is domain specific, but there are some general requirements. Well, it definitely is domain specific, but for the Metropolis algorithm to work, there are just some general requirements. Like I think the probability distribution of the probability of obtaining the next, let's say, the candidate X sub Y plus 1 given current candidate X sub Y should be the same as obtaining Xi given Xi plus 1, right? And in the instance with our travel and salesman approach, that intuitively makes sense. That is true. And I think that's the only real criteria for the Metropolis algorithm to work to simulate the probability distribution, the Boltzmann distribution here. So yeah, but the actual implementation is of course context dependent.
Okay,
but the approach is quite general. Yeah, I thought this was really cool.
You said you reversed the whole substring, right?
Well, the substring, yes.
Yeah.
Not just the tree indices, but the substring.
Yeah.
Uh-huh.
Yeah, this is very interesting.
Okay. Well.
Yeah, I'm just trying to think through. Do they provide so they give a really neat analogy, I think, as you were saying, to metal cooling. So you heat it you heat it a lot and then you start to cool it. But you don't just cool it to, the temperature that you want. when you're done, you cool it, then heat it up, and then cool it down to quote unquote remove impurities, which I think they were saying, sort of casually.
Right.
I'm wondering though, is the metal procedure more precise? Like, is there some annealing schedule that they follow? Is that informed in some way?
Yeah, that's fantastic. I think there is a paragraph somewhere where they say let's essentially T is a hyperparameter. What they call the annealing schedule is a hyperparameter.
Yeah, I saw that word in there. That's why I said I did not come up with that word.
Yeah, you just got to figure it out on your own. No, there's absolutely no guidance on how to pick that. When I was implementing this, so I had to try a few times for it to start working properly. But so I did sort of at every temperature, I simulated 1,000 candidates using the Metropolis algorithm, right? And once I was done with 1,000 candidates, I would lower the temperature by 1/10,000th of a degree, starting at temperature 10. And for 500 cities that worked. So this definitely might not be applicable at all to some other sort of problem. This is, I don't know, just luck.
Yeah, like is there, like for metals, right? Is there some schedule that people have figured out? Did they just try a bunch of stuff and one worked?
Well, right,
I guess
I don't know.
Yeah, that'd be interesting.
That's a good question, right? Maybe you could take this analogy further. The Wikipedia article has some advice on how to pick the annealing schedule, but what I'm personally interested in is if they first got the idea that we can do iterative improvement, but occasionally move upward, and then they figured out that, oh, okay, that's actually that's consistent with what happens in physics, or they actually got the idea from physics. I'm not sure which way it was in reality. It could be either. I don't know.
I'm seeing Lennon Kernighan here for that subset movie you described. Lennon Kernighan apparently introduced that trailing salesman like optimization step where you reverse a set of moves when doing some kind of iterative random thing. And Kernighan, I'm pretty sure is Brian Kernighan. I looked it up. He's that
guy.
Yeah, the Unix guy who worked with Ken Thompson.
Yeah. Oh, yes, that is
programming language. Okay. Yeah, so many famous names.
Okay. Mm-hmm. Okay.
Yeah, cool. This is really cool. I'd wonder if you could run, because you made a GitHub repo on this, right? You should paste it, by the way. It was in Rust, by the way. I've actually not really worked with Rust, so I think people would find it pretty fun to go through. But I'd be curious if we could run it on like a data set of like solved traveling salesman problems.
Exactly. I really wanted to. I couldn't figure out to find one that worked. We could do it.
I'm sure there's like one where it's just like gives you the list and then the optimal path, and we see how much better or how close this is. Yeah, I'm sure we can get some kind of curve. Like what is it? What are the important parameters? Number of cities. So how the algorithm like the best version of the algorithm. Let's say there's a set of hyperparameters you're going to search over. The best version of this algorithm over the number of cities, and then how that grows, and then also for different, I guess kind of this graph you have here, which is just like as you change your temperatures, how does the distance change? Although it's going to be clearly, something of this shape.
Yeah. So their target metric was the average. They saw the total distance divided by the number of cities, and they said that less than 0.95 is good. And I think I got to, it's 450 over 500. So yeah, it was about 0.95 for me too. Well, I guess so. Since 1983, I guess I didn't make that much progress, right? But it's fine. It's fine.
I also wonder if you can get any kind of, because it has a nice, I guess, physics draw. I wonder if it has any kind of like guarantees or something, because they're mentioning at the start, right, that like worst case analysis is stupid and not actually relevant. And average case analysis is a lot harder to do. I think we did that sometimes in combinatorics. We talked a lot about worst case analysis, but average case, yeah, actually for a lot of the ones I know of, there's one in biology. I'm trying to remember. They taught it in the elective class for bioinformatics 466. this iterative algorithm, greedy algorithm that had a worst case analysis that was pretty cool to work through. Did they do any kind of like average case analysis or even worst case analysis?
No, I don't think there's any analysis.
Yeah, I
on
don't know
that.
if you can do one, but yeah.
So I asked myself the same question. I honestly don't know if it's even possible. You can just kind of give it a try.
Yeah. Yeah.
Well, the variance of the greedy. Yeah, let's just for the greedy algorithm for the simulated angle. I don't know. It's probabilistic. It's literally yeah. I don't know. But mhm. I'm glad you guys attended. I guess we'll see each other next week then.
Yeah, that was really well presented. Nice job. It was a tough, I think you explained the background pretty well. I think it made a lot of sense.
Thank you. Thank you. All right. Lots of fun. Bye.
See ya.
Thank you.
Thank you.
See you guys.